Hi, welcome back for Chapter 2 example problems. Here we'll take a look at a few problems involving the parts of the atom, average atomic mass, also known as atomic weight, and then some naming and formula writing. All right, so if we look at this, for this first one, 2.24, we're looking at this atom of copper, which has a mass number of 63. And so first off, it wants to know how many protons, neutrons, and electrons are in this atom. The protons are going to be always equal to the atomic number. So just find copper on the periodic table. You'll see that it's number 29, kind of right in the middle of the table, which means it's 29 protons. That's it. No other work needed to do. Just find that number in the box. For neutrons, neutrons are always equal to the mass number, so given here is 63, minus either the atomic number or the protons, but same thing. So 63 minus 29, and that means it's going to be 34 neutrons. Let's go ahead and circle those answers. And then electrons, because there's nothing written here in the top right corner where charge would go, electrons always start out equal to the protons, so there would also be 29 electrons, and there we go. All right. B then, it says, what would the symbol be if we remove 2 electrons? And so the thing to remember is that electrons are negative. They have a negative charge, which means if we get rid of the negative, we leave behind positive. So if we take away 2 negatives, we're going to have 2 positives left over. So we would still have our 63 as the mass number. We would have the copper for our element, but now it would be a positive 2 charge. So it would be 2 plus in the corner. If you write plus 2, I'm not going to mark you wrong, but officially when we write charges in the corner, the magnitude goes first, then the sign. All right. And then the final thing, it says, well, what would the symbol of copper be if we have 36 neutrons? Well, again, the mass number is always equal to the protons plus the neutrons. Well, the protons are still 29. If it's copper, it is always 29, no exceptions. But now they've told us there's 36 neutrons. Well, that means it's going to equal 65. And so if we do that, well, that means we'd have copper as our symbol, and we would put 65 up in the corner, and that's the symbol of that isotope. Okay? So hopefully not too bad. Just remember your definitions about what number always has to equal something else, or at least what number always starts equal to something else, and these problems kind of solve themselves. All right. Next problem, it says we have 2 isotopes of copper. Hey, we just found them, 63, and hey, look, there's 65, like we found. And they tell us how much they weigh exactly and what their percent abundance is. And they want us to calculate the atomic weight. That means what's the weighted average of all the isotopes. So in this case, there's only 2. So for that one, we just take each isotope and how much they weigh. So we have the first one, 62.9296 AMU. And we will multiply it by its percent abundance. But we always make it the decimal form, just to make it easier for ourselves later on. So that just means move the decimal 2 spots to the left, divide by the 100. So this will be times 0.6917. We're also going to take the second isotope, 64.9278 AMU, multiply by its abundance, but move that decimal twice. So 0.3083. And then once we get those 2 answers, we're going to add them up. So over here on the right, I'll put the answer. So calculators out. 9296. 6.6917. And so this first one is 43 point, I'm going to round it to 53 because we only have 4 sig figs for our percent. So we'll only have 4 sig figs for our total, but that's still AMU, right? The AMU didn't cancel with anything. If we do our next one, 64.9278 times 0.3083, we get 20.02 with rounding AMU. And so now, well, we said we were going to add these together, so we just add these two together. So that's 63.55 AMU. And conveniently, if you look on your periodic table in the box for copper, 63.55 is what you're going to find there. So that's all you got to do. If there's more isotopes, just add more lines. If there's 4 isotopes, yeah, it's annoying. You got to do it 4 times, but that's all you've got to do. All right. Next up, we're going to predict ionic formulas. The book makes a big point of this, and I know I put this in the problem set, where just to get used to, if we have charges given, or once we know what the charges are, how do we do that? We talked about this in lecture with the crossover method, that just the number value, don't worry about the plus or minus, but the number value will switch and become the subscript of the other ion. So in this case, this -1 comes over, we'll have 1 chromium. This 3 comes over, we'll have 3 bromines, and that's it. There is a final step to check to make sure we can't reduce, but if you got 1 of something, you can't reduce. So this is 2.62, that was A. B, same thing, okay. Now we have 2 numbers that aren't just 1. The 3 switches, the 2 switches, okay, so we'll have 2 of those iron atoms. We'll have 3 of the oxygens. That's it. We can't simplify 2 and 3, call it good. Now this last one I picked because this NH4+, that's a polyatomic ion. It has to stay together. At no point can you ever change the formula of a polyatomic ion. Same thing here, this is phosphate. But we've got to move this 3 over. Not the 4, it's always the charge, so it's the 3. But how do I put a 3 over here? I can't change the 4, do I make it 12? You put the entire polyatomic ion in parentheses to say this is one thing, it sticks together. We put the 3 then as a subscript right next to it saying this 3 applies to the entire thing. And then there's a 1 there that switches over. So we just have 1 phosphate, 1 PO4. There's the 3. So you always check, can I simplify? None of these did. But if you get something that's 2 and 2 or 2 and 4, that can simplify down. But if you have a polyatomic and you need more than 1, you put in parentheses. If you only have 1, leave it alone. When people see PO4, oh yeah, that's phosphate. It has to be. All right. For this next bit, before we get to the practice problem, I'm just going to review what we're looking for. How do we tell the difference between things that are ionic, covalent, or an acid? So if something is ionic, the clues that we look for is that the first element is going to be a metal. And that applies whether it's a transition metal or a regular metal. It applies whether we're looking at the formula or the name. You look at the first thing you see, and if it's a metal on the left side of the periodic table, left side of that staircase, then it's just assume it's ionic. There are exceptions, but in this chapter, assume it's ionic. Other things you can look for, if it's a transition metal, you might see a Roman numeral. So that's a giveaway of, oh, only metals get Roman numerals. If I see a Roman numeral, I have a metal. If I have a metal, it's ionic. The third thing you might see, if you have a polyatomic at the end, you might see 8 or ite at the end of the name with this, the non-metal. But if you see 8 or ite, that's a clue. Hey, that's a polyatomic ion. That means it's ionic. All right. For covalent compounds, then, the first thing you're looking for, again, whether you're looking at the name or the formula, is going to be a nonmetal. So if you see the first thing, hey, that's oxygen, it's nitrogen, it's carbon. Those aren't metals. Okay, assume it's covalent. The other thing that you'll look for as a clue, especially if you're looking at the name, are prefixes. Ionic compounds don't use them. There's a few polyatomic ions that have them built in, but they're not in our need to know list for this chapter or even this course really. So if you see a prefix, if you see di, tri, tetra, then 99% of the time it's covalent. Just go ahead and assume that. Okay? And so that's how you know that it's a covalent compound, one of those two methods. If it's an acid, well, then it's easier still. The first thing in an acid, 98% of the time we'll call it, is hydrogen. If you see an H in front, it's guaranteed pretty much to be an acid. There's a few exceptions if you have some weird gases, but if you see H in front in this chapter, assume it's an acid. Or, even easier, if you see acid as part of the name, hydrochloric acid, formic acid, sulfuric acid, if you see the word acid, it's an acid. So here are just real short cliff notes of what am I looking for to first be able to say, when I see this thing, how do I know which set of rules to follow? Okay, so let's do a couple examples. These were pulled from various problems in the chapter, but we'll just kind of look at them to see this process. So aluminum, we look at that first thing. Aluminum is a metal, so right away I know that this thing is ionic. I will then go ahead and say, okay, let me look that up. Aluminum is Al. Based on its position on the periodic table, I count back to the noble gas to figure out how many electrons the metal loses. It will lose 3, so aluminum will be 3+. We then look at hydroxide. Now this is one you got to know. It kind of looks like hydrogen, kind of looks like oxygen. It's actually both. It's a polyatomic that still ends in "ide," so that makes it a little weird. But just memorize hydroxide. Just go ahead and do it. It's OH with a -1 charge. That means when we then crisscross these charges, I'll have 1 aluminum. I'll need 3 hydroxides. And like we said, a polyatomic cannot change its formula. You have to keep it together. So we put it in parentheses, OH3. There's our final answer. Okay. The next one, we have bromic acid. Well, right there, it's an acid. Because, well, it just is. Now, here we have to follow our rules from the, I think it's the last part of chapter 2. There's no hydro out in front. That means this is not a binary acid. It's not just H and an element. This is going to be H and a polyatomic ion. So, and then we say, okay, ic is connected with the ions that end in 8. So I'm looking for bromate. Right? I'm changing that ic to the 8. I'm looking for bromate. Well, bromate is BrO3 with a -1 charge. Right? And then once I have that, the rule for acids, how many H's do you put in front? It's the same number of H's as the charge, so if that's -1, we need 1 hydrogen ion out in front. So our final answer, HBrO3. All right. Finally, we have XeO3. We look at that first thing. I just realized this is actually a, well, we'll have to mix this up. Sorry, I didn't give a name, I gave a formula. But Xe, well, that's going to be a nonmetal. That means this is covalent. We're going to look for prefixes. Xe is xenon. So we'll go ahead and put that in. There's only one of them, so we don't put mono with the first thing. If it were to one of the second, we would, but we leave it off here. Now we have 3 O's, and so that would be trioxide. The 3 becomes tri. Right, sorry about that. So imagine this in reverse. Xenon trioxide. Hey, xenon's a nonmetal, so it's covalent. That means we don't switch anything. Okay, trioxide, that means there's 3 O's. That's how it works in reverse. All right, naming examples. So now if we get formulas, how do we give the name? So here's N2O4. Again, we look at the first thing. It's a nitrogen. That's a nonmetal. That means this is going to be a covalent compound. That means we're not switching anything. We are just simply saying, what's the element? And do I need a prefix in front? This first element is nitrogen, like we said. There's a 2 there, so yes, we do need a prefix. This will be dinitrogen. And then we have O4. So O is oxide, 4 is tetra. And then there's that little abbreviation we do with oxides. We leave off the A of the prefix, so it's just tetroxide. Not tetraoxide, tetroxide. And that's it. Notice for covalent, we don't simplify if it's 2 and 4. We leave it 2 and 4. All right, second one, we have Fe. We looked that up. That's iron. Iron is a metal. It's a transition metal. So that means this is going to be an ionic compound. That means we're just going to name the metal, and then we're going to name the nonmetal. But because iron's transition, we do need to get the Roman numeral. We got to say, well, what charge is that iron? So we go through the first thing. We'll just say, okay, well, Fe is iron. It's a transition metal. We'll leave a parentheses space there to say, I'll put a Roman numeral in here once I know what it is. ClO4, that's a polyatomic. We'll learn that that is perchlorate. And now we go back and say, okay, gotta figure out this Roman numeral. We don't know what the iron is, but we do know perchlorate. We can look it up in the table in chapter 2. Perchlorate has a -1 charge, but there's 2 of them. So that means there's another -1. The rule with ionic compounds is they always add up to 0. So if we have -2 overall, we need a +2 to cancel that out. So if the iron's +2, we put a Roman numeral 2 in that parentheses. And there's the answer to that one. Okay, for our third example, the very first thing is an H. That means we automatically know it's an acid. Now this one, it's H and an element. So H plus element equals use that hydro prefix. So this will be hydro, bromine becomes bromic, hydrobromic, and then never forget, always end with the word acid, hydrobromic acid. All right, so hopefully this little tutorial helps you out with chapter 2. And it's a tricky one. The naming, you gotta get. That's definitely something that does not go away. A lot of later chapters are dependent on having the correct name or the correct formula from the name. Now that one's a little more important in order to do the later stuff. So make sure you practice chapter 2. I'd encourage you to do more problems than what I assign in the problem set. Anything that's color-coded in the end of chapter problems will have the answers in the back. Make sure you get those. All right. Have a good day. See you in the next video.